Hey everybody, welcome back to AWS What's Next. I'm your host Shashank. If you're just tuning in, this is your opportunity to learn more about some of the services and features we launched at reInvent. And in this specific session, we'll be talking about a very exciting topic, which is distributed training with Amazon SageMaker. To tell you all about the new capabilities that we launched this reInvent, I have here with me Aditya. Aditya, do you want to quickly introduce yourself?
Thanks, Shashank. Hi, everyone. It's great to be here. My name is Aditya Bindal. I'm a senior product manager with AWS, and I'm excited to talk to you today about distributed training.
Awesome. Welcome, Aditya. This is a topic that I'm very excited about, having spent some time in this space, distributed training. Now, if there's one thing that's been consistent in the machine learning space is that data sets have been getting larger, models have been getting bigger, and which means you need more compute and you need to be able to scale. And this has been consistent across computer vision and natural language processing, recommendation systems, and probably many other applications our viewers deal with on a day-to-day basis. So to start off, would you like to just tell us first about what are the key challenges with scaling machine learning when you have large data sets and large models, and what have customers been telling you is the big challenge that they face?
Yeah, I think you put it well. Let's start with the research side. So, researchers building new neural network models in TensorFlow, PyTorch, MXNet, they found that they can get much higher accuracy by using significantly larger training data sets, especially in computer vision and natural language processing. But they've also found they can get higher accuracy by using much bigger neural network models. We used to talk about
Right.
parameters in millions, and now we're talking about hundreds of millions, billions, and in some rare
Mhm.
cases, even hundreds of billions. So the sheer
Wow.
scale has become a lot bigger than anyone expected at the time. And that's produced a lot of challenges when you try and use some of these state of the art neural network models and techniques
Mm,
in your own workloads. So there are two in particular customers told us about. One is when I'm training with lots of data, it takes
mm,
a long time to train, and I need to scale out and parallelize my training on a cluster of GPU machines in order
mm,
to get my training results quickly enough. And if you're a data scientist or a team of data scientists, the longer it takes for those training results to come, the slower your overall time to market, because you need to now
mm.
wait for the results from that first run before you can learn, iterate, maybe make some
Right.
changes to the architecture of the model, incorporate new data augmentation, and then kick off a new run. If you can do that once a week versus once a day, that's a huge
That's
impact
huge.
on your velocity.
Yeah.
That's one
Especially
problem.
when you're
The second
experimenting.
problem is exactly right. Velocity matters because you need to iterate fast and
Mm,
incorporate everything you learned from the last run of the model.
exactly.
And the second pain point customers told us about is model sizes when they become so big, they don't fit on a single GPU's memory. So if they
Mm,
don't fit in a single GPU's memory, you can't train such a big model, which means you can't get that same level of accuracy. So you have to
mm,
compromise. You have to either reduce the size of the model, or you need to try and implement a technique called model parallelism, which
mm.
requires you to split the graph of the model across multiple GPUs, and that's a very complex, time consuming, and sometimes inefficient procedure. So these are the two
Mm.
pain points customers really told us about. How do we do this better so we can leverage state of the art techniques?
Yeah, especially data parallel is something I know people use because there's some libraries out there that help you with it, even though they have to sometimes manage their own infrastructure or figure out how to do this. But model parallel is such a niche thing that it's very hard unless you actually know hardware and
Yeah.
your data and your model and how to split it. So how are customers dealing with this today? Both these challenges, before this new capability that we'll just talk about, what were they doing?
Yeah.
How were they spending time to actually achieve these results?
Yeah, great question. So let's start with data parallelism. With data parallelism, there are some great open source solutions that our customers have been using. They would use sometimes the inbuilt solutions in deep learning frameworks such as
Mm,
PyTorch DDP,
right.
TensorFlow's multi-worker mirrored strategy, or they would use Horovod with
Or what?
TensorFlow, PyTorch, and MXNet. And a big pain point when you scale out these algorithms to, let's say, 64, 128, 256 GPUs, is the scaling efficiency. So in an
Mm,
ideal world, if it takes 8 hours for one machine to do something, it should take 1 hour for eight machines to do the same thing. But
right.
in reality, you don't get that linear scaling efficiency because
Mm,
there's a lot of overhead when the machines need to communicate with each other and synchronize gradients in each
all
step.
the
So that
communication.
exactly. So that communication between machines is what ends up becoming expensive. And we have a very specific topology in AWS. So the algorithms that are out there today, the techniques that are out there today, they don't fully utilize the infrastructure
Mm,
and the network that AWS offers. And we can make something that's faster, more stable, and more fault tolerant.
mm. So let's talk a little more about what we launched this
Yeah.
time around. I know SageMaker has had distributed training for a while now, so you can actually set the number of instances or GPUs you want, and you can bring in your script, maybe Harvard enhanced script or something like that, and you can do that. What is different with what we launched this reinvent, and what's new that we launched compared to what customers were able to do before?
Yeah. So there are two paradigms in data parallelism. There's a parameter server approach. This is what TensorFlow had originally launched. And you have a single parameter server, a set of parameter servers that do that gradient synchronization from all the worker GPU nodes. And then you have a ring all reduce, much like HPC applications where you use MPI to let the GPU machines communicate directly with each other. And SageMaker has supported both for quite some time now. You could
Hmm.
use parameter server based distributed training approaches. You could use ring all reduce. What we've launched today on the data parallelism side is a new library. It's called SM distributed. And to
Hmm.
use this, you would just use SM distributed.dataparallel that
Hmm.
combines the best of both worlds. So parameter servers would get bottlenecks become unstable as the number of machines grew because everyone had to communicate with these
With
parameter
one
servers,
parameter. Okay.
and
Mm,
the amount of data being sent and received from the parameter server, each parameter server, was unequal, creating bottlenecks. And so what we did was we rethought this from scratch and we took the best of both worlds. So we borrowed a few concepts from the ring all reduce approach and a few concepts from the parameter server approach. So we now have a third
mm,
option to use SM distributed, which implements an all reduce that's optimized for the infrastructure network that AWS offers.
mm.
So that's on
So
the data
Aditya, this
parallel
seems
side.
like novel work, right? This is new stuff.
Yeah, and in fact, you may have seen some of this work in reInvent keynotes. So last year
Mm,
we had demonstrated the fastest training times in the cloud on Moscow CNN and BERT. And this
mm.
year, during the machine learning keynote with Swami, we again demonstrated the fastest training times in the cloud with Moscow CNN and T5. So SM distributed is that underlying technology, which is now available in a very simple to use API for all of our customers.
That's awesome. You also mentioned model parallelism. So what did we launch there?
Yeah.
Libraries or approaches?
Yeah. So let me start with what customers were doing before. And this is an interesting one.
Mhm.
As you pointed out, model parallel is a little bit more novel. So
Mhm.
we actually had a lot of customers that wanted to train bigger models, but the investment in
Right.
expertise, time, weeks of development to figure out what's the best way to split this billion, tens of billion parameter size models was never justifiable. So they would end up training smaller flavors of the same model. So instead of
Mm,
training GPT-2 XL, they would train maybe a smaller variant of that same
mm.
model. And they would know they can get higher accuracy, but that just became a huge investment that they didn't want to make.
All right.
So we've launched a new library again under the SM distributed umbrella called SM distributed.model parallel. And this
Uh-huh.
is a fully managed solution for model parallelism in SageMaker. And the way it works is you give Amazon SageMaker your training script, your model, making minimal changes that we'll just see in a demo in a few minutes.
Mm.
And SageMaker will profile your model and figure out the best way to split the model up across multiple GPUs and set up an efficient execution pipeline that makes the utilization of your GPUs go up.
One of the this reminds me of the actually the early days of deep learning, which coincidentally happens that AlexNet, when AlexNet came out, which revolutionized and brought deep learning to the mainstream, it happened to be a model parallel approach that he used because back in those days, GPU memories were small. So he had no choice but to split the model. And if you look at the code, there's a lot of code with custom GPU implementation.
Yeah.
And that's the key, I think, right? The customers don't want to be able to do this manually. And secondly, they may or may not have GPU expertise to understand, GPU memory limitations and how to split. So this is, I think, a huge benefit.
Yeah.
So let's talk about who this is for. The way you described it seems like it's easy, quick and easy to use for a developer data scientist. You don't need hardware expertise. Is that right?
Yeah, and going off of your last point, a lot of the model parallel implementations we saw in research were from a handful of companies and research
Mm,
institutes that had people that really deeply understood uh,
right.
low-level programming and operations for GPUs and model parallel operations. And what this does is it makes it accessible to any developer in TensorFlow and PyTorch that wants to
Mm,
incorporate state-of-the-art into their applications, into their workloads. So if you are training, let's say, some natural language task and you want to use the latest NLP model with some X billion parameters, these capabilities will make it easier for you to use because you don't need to have that same ground up understanding
mm.
and deep expertise in how to partition graphs and place them and set up execution pipelines. All of that complexity is fully automated by SageMaker.
That is awesome. This is one capability that I'm excited to try out because this is on AWS today. You can get P3DN or P4 instances with multiple GPUs in an instance, and you can previously had to do a lot of work to take advantage of all the GPUs. And today, with
Yeah.
this new capability, you can make sure that you're keeping the utilization very high. That is how you can save cost by making sure your utilization is very high, and you're utilizing fully, and combined with capabilities like the new SageMaker debugger monitoring capability, you can actually observe this is huge in my
That's
opinion,
right.
and this will not just help them get better accuracy but also potentially save costs by making sure their resources are being utilized.
Yeah, absolutely. And one thing we've also heard from customers is they get to now pick and choose the GPUs that are exactly right for their large model training jobs.
Mm,
So for example, if I just need to split the model up, but I don't really want to train with multiple machines, I don't care about the network between my GPU machines. I'm only using one instance with 8 GPUs. You could save
mm,
money and use maybe a P316X instead of a P4D or a P3DN
right.
because you just need the model parallel capability, which SageMaker now provides, without some of the other premiums that you aren't using for that particular workload. And then for a
Yeah.
workload where you are using a cluster of machines and you want a high performance network, then you use the P3DN or the P4D instances.
That's awesome. You mentioned some of this is original work, right? In the sense you took the best of ring all reduce approach, best of parameter store approach. Are there any other things that you want to talk about? The innovations that went into building this capability and make it easily available for SageMaker user with a few lines of code?
Yeah, I think there's a few that I'd like to highlight. So on the data parallel side, there's a new concept we came up with and implemented called a balance fusion buffer. And the way
Hmm.
it works is we have a balance fusion buffer that would copy fuse gradients from GPU to CPU, and then it would send it to each parameter server in equal amounts. So this overcame the key shortcoming in parameter servers where the amount of
Hmm.
data being sent and received was unequal, which created uh, instability and bottlenecks. Now all the parameter servers were getting exactly the same amount because the balance fusion buffer was guaranteeing that.
Right.
The second is on the user experience in the API side. So we took a goal for our teams to not introduce any new concepts, any new terminology. Our
Hmm.
customers already knew how to use Horovod in
Right.
TensorFlow and DBP and PyTorch. So we had an API specification that mimicked what they already knew. So they don't need to now learn some new SageMaker specific API for distributed
Right.
training, the code change involves just changing the import line and everything else stays the same. And we'll see that in a few minutes in the demo. On the model parallel
Yeah.
side, just very quickly, go ahead.
Uh-huh. No, good, good. This is exciting. I want to hear from you.
Uh, on the model parallel side, I think there's again two things. The first is that one of the big pain points when you implement model parallelism is where to partition the model. But even if you figure out what's the best way to partition the model, where you're trying to
Mm-hmm.
balance two things. One is you want the compute to be relatively balanced between all the GPUs in your cluster. And the second is you want to minimize the amount of communication that's needed between machines. And
Mm-hmm.
so, even once you've figured that out, you then need to decide how to set up your pipeline, how to pass batches onto your GPU machines so that you can get high utilization. In the extreme case, you would have very low utilization because imagine if you have a four-layer model split across four GPUs. So when batch one is going through GPU one, two, three, four,
Mm-hmm.
the other three GPUs at any point will be idle. So to fix this, we actually take that mini batch and we split it into even smaller micro batches. And then we
Mm-hmm.
sequence the execution in an interleaved pipeline so that while, let's say, micro batch one is doing a forward pass, micro batch two may be doing a backward pass. And so we allow the
Wow.
GPUs to all be active at the same time, and that increases GPU utilization, reducing your training time, reducing your build.
Wow, this is some really innovative work. I was just visualizing what you were talking about, and essentially, model parallel is in some sense sequential processing, right? The models are parallel, but the
Yeah,
data still goes through each of these GPUs in sequence, and
exactly.
utilization can be a bottleneck. And you've done all this good work to make sure the utilization is high. This is awesome, and the best part, the I was about to interrupt you and I couldn't contain myself, because the best part of this is, I think this is a classic example of working backward from customer pain points. And someone like me, I'll be able to take advantage of this without being an expert in hardware, or without being able to um, implement all these model parallel and keeping utilization high and all that. So this is exciting, Aditya. And I think I'm all the more excited now to see this in action. I think this is demo time. Let's jump right into it.
Let's do it. Great. So you can see my screen. So, Shashank, since you were visualizing it in your head, I'll just quickly show you. This is what it looks like. So you're splitting up these mini batches, and you have two GPUs in this example, and you can then overlap so that the forward and the backward of each micro batch is passing at different
Mm,
times, increasing the overall GPU utilization. So that's how we look at it. We also published a deep dive blog on how we use the same underlying technology for SM distributed to achieve record training times in Muscar CNN and T5 this year. Okay, so let's get started. I have a SageMaker Studio open over here, and I've cloned the SageMaker examples GitHub repository, which, if you're not familiar, has a lot of examples on how you can use SageMaker for model building, training, and inference, and
mm,
many other capabilities in SageMaker. So let me now navigate to this new section we have for SM distributed on distributed training. And we'll take a PyTorch example. Let's start with data parallel, and we'll do a
mhm,
simple hello world with MNIST. So first things first, you'll find these example notebooks, and these are the best ways for you to get started. Let me walk you through the estimator first. If you've used SageMaker for PyTorch, this should look very familiar to you. What
mm,
you're doing here is creating a training job in SageMaker using the PyTorch estimator. So you're saying I want to use version 1.6 of the framework, Python 3.6, and we'll look at this entry point script in just a minute where we make some of the code changes. And everything is the same except for this last argument over here, where we say the distribution is SM distributed. So this is
mm,
how SageMaker knows that you want to use the new SM distributed library instead of DDP or Horovod.
uh-huh,
And we want to use the data parallel engine as opposed to the model parallel engine that we
mm,
would see in just a few minutes. And we just want to enable that SM distributed dot data parallel engine. And that's it. Everything else that you do in SageMaker is exactly the same. You would call fit and then you would have a model artifact. So now
And
let's look at the
Aditya,
actual
just
training code.
just for some of the viewers who've not used SageMaker, so very quickly, all they have to do is bring in their own training script and use the PyTorch estimator, provide their training script, specify what kind of instances they want, how many instances they want, and SageMaker manages the training instances, spins it up, finishes training, copies data from S3, and puts results back in S3 and shuts it down. That's like fully managed experience
That's right.
for training with SageMaker for those of you who are new to SageMaker. And with this, now we are going to see with minimal code changes how we can do data parallel and model parallel.
That's a
Go.
great call out. And in this example, we're using two P316X instances.
Mm,
So we don't have to create these instances in a cluster and ensure that they're network. SageMaker does that
mm.
for you. This is
That's
a
a
fully
total of
managed
16
experience.
GPUs, right? That's a total of
That's a total
16
of 16
NVIDIA
GPUs. That's right.
V100 GPUs. Okay.
Yes. So now let's look at the training script. And if you've used DDP and PyTorch before, everything you see here would look very intuitive and obvious to you because we followed the same API
Yeah.
specification
Mm,
as DDP. So instead of importing from torch.distributed data
mm,
torch.parallel and importing that DDP, we have the SM distributed data
mm,
parallel and our DDP, as well as the same disk, the torch.distributed that you would use with
mhm,
SM distributed instead. So now, just like you would have done when you use torch.parallel, you would initialize your process group. The rest of your
mm,
training script stays exactly the same. So we're making no change in the core training loop. We aren't changing the way you do evaluation. We aren't changing the optimizer you use. You don't need to make any changes to the way you compose that neural network.
mm,
Um, and then when you get to defining some arguments that are used for the distribution steps. We
mhm,
get the world size, we get the rank, and we get the local rank.
mm,
So we can get the local rank for each GPU. We use the same disk that we defined earlier,
mm,
and that's coming from SM distributed. So again, if you've used DDP, this is
mm.
exactly the same. If you were being very lazy, as I've been, sometimes you could literally just change the
Just
import
replace.
statement from
Yeah, yeah.
torch data parallel to SM distributed, and you wouldn't need to make any other changes in your training script.
Yeah,
And
I
then
was
once you're
wondering about
ready,
that too. Can a user just simply replace because you have API compatibility, right? You just replace, and if things should work, it might be one of the first things to try before actually um, going through the rest of it, right? See
you
if it.
you could do that. We always like to change it explicitly so that
Mm,
we know where it's being used, and
right,
that it allows you to explicitly go through and make sure a training script is doing exactly what you expect. And then finally, we wrap our model in DDP the way you would
right.
in PyTorch today. And then we're ready to send this training job to SageMaker to train it on two P316X instances. So that's all. And before we move on to model parallel, I just wanted to quickly show you some benchmarks. So
Oh wow. Perfect. Mm,
we've used SageMaker's new distributed training library for data parallelism and compared it to what our customers were using previously. So here you see an example in NLP using the popular BERT model. And then you also see an example with MaskRCNN, which is a popular semantic segmentation model, or I should say instant segmentation model
mm,
used by our customers. And there are two things you'll see here. One is the throughput, and the second is the scaling efficiency. So these numbers are obviously related. What's interesting here is that you have some examples, like for let's take BERT scaling efficiency on 8 nodes. You go
mm,
from 67% to 78%. And what
mm,
that does is when you go from 67 to 78 is you're now no longer facing a trade-off between time and cost. Or if we look at the 4 node, 55% to 84%, you're able to you're able to decrease your time to train significantly with only a very minimal increase in the cost. And then you see on throughput, we observe increases in performance on mask RCNN across different cluster sizes, as well as on BERT. And so we find this is quite robust. It's not specific to any neural network architecture. It's not specific to any
mm,
framework. we see these kind of improvements broadly on TensorFlow and PyTorch.
Now, Aditya, something that I think we should highlight in that in the benchmarks you just showed, and that's not very evident, is the cost savings that come with scaling efficiency, right? Previously, if your scaling efficiency was low, which means you're actually underutilizing a lot of the resources, so higher scaling efficiency is automatically translates to some cost savings because you just don't want to get better throughput and faster training but poor scaling efficiency. That's not good too. So this is nice to see
Yeah,
that you're making improvements on both fronts here.
it's a great call out. High scaling efficiency allows you to keep scaling out without incurring any significant increase in cost,
Mm,
to basically as much as you want. The stopping point would be when training time is no longer a bottleneck in your
mm,
development. So, for example, if you don't need to train once an hour or once every 2 3 hours, there's no
mm,
benefit to you to scale out that much. But if you need to
exactly.
train once a day or twice a day, then
Mm,
you want to keep reducing training time till it's no longer a bottleneck in your development.
that's a good point. Yeah.
So let me quickly
Especially
also
with
just show
model.
you SageMaker model parallel. So now, just like we saw with data parallel, the estimator, again, would use PyTorch endless as a nice and simple hello world example. Can you still see my screen? Yes, great, you
Yeah.
can. Um, so everything else is the same. We specify in that PyTorch estimator when we create our SageMaker training job, what framework version, Python version, and in
Hmm.
this example, we use one P316x large instance. We're not
Mm.
trying to do a hybrid of data parallelism and
And
model
model.
parallelism across multiple machines. We'll just use data parallelism and model parallelism in one P316x GPU instance that
I
has
assume majority of
eight
the use cases
P1.
fall into this approach, right? Where you try to utilize all the GPUs on a single instance for model parallel.
They do. I think it also depends on what your goals are. If you're training
The
this model
specific use case.
once, then maybe you don't care that much about a slightly longer training time. If you're training this model once a week or twice a week, for example, then you may want to do data parallelism across multiple GPU
Mm,
instances with hybrid model parallelism as well. So let's go through quickly on what the distribution argument looks like. So you saw in data parallel, we use SM distributed data parallel. Here we're using model parallel. And there are
mm.
some specific parameters for model parallel. So we want to say how many micro batches we'd like to
Mm,
use. And we have some guidance in our documentation on how you should think about
mm,
these parameters and when you should use which values. Our placement strategy, our pipeline. So this interleaf
mm,
pipeline is what gives us more GPU utilization. And then
mm,
what do we want to optimize for, speed or memory? So we may make different decisions on partitioning if your goal is to just train this model faster or to utilize as much GPU memory as possible.
mm,
And again, depending on your use case, which we'll address in detail in our user guide, you may choose one or the other. And then how many
mm,
partitions you would like to make. So in this example, we're saying two, which means we would do a hybrid of data and model parallelism where we'd split the
mm.
model across two GPU devices 4 times in one instance. So that's 4 times
Ah, got
two
it. Okay.
hybrid data and model parallelism. And then we're using the native DDP engine in PyTorch for data parallelism. So now let's look at the training script quickly.
It's nice
And
that doing
I know
hybrid is
we're
so
about to
easy.
run out of time.
Yeah.
Yes, exactly. That was one of the goals we had for this. So for most workloads and models, you would need to make fewer than 10 lines of code change, and these code changes would be very intuitive in terms of how you use TensorFlow and PyTorch today. So we import the SM distributed model parallel library. We'll call it SMP. And then I'll show you the only places we need to do it. So we have this decorator where we would say SMP step, and this is
Mhm,
how we would get back the tensors and make decisions on how we're partitioning the model. We would also have the SMP step decorator for evaluation, which you would also have as your own core function defined here. So you don't need to make any change, just like data parallel, to the core training loop and training step that you defined, to the optimizer you use. All of that stays the same. All you're using is these decorator functions outside, which allows you to which allows SageMaker to make those partitioning decisions
mm.
and set up those pipelines for you. And so I know we're almost out of time, We have a new user guide to use these SM distributed libraries, and they walk through some core concepts in distributed training. So when how you should think about batch size, when to use data parallel, model parallel, both learning rate, issues and convergence you might hit, some advanced concepts on mini batches and micro batches and how you should think about them,
Mm.
different strategies and which workload might work well for each one. And then we have deep guides on how to use data parallel and the model parallel SageMaker libraries that we've launched.
That's awesome. There you have it, folks. This is the new distributed training capabilities with Amazon SageMaker for both data parallel and model parallel. Thanks, Aditya, for the code demo. And as you know, the notebook and the code files are available on GitHub with the rest of the SageMaker sample. There's also a blog post which talks about performance scaling benefits that we saw, and the new user guide which talks about how to choose some of the parameters, as this may be a new concept to many of you. I know I'm excited. I'm going to try this after the stream. So thanks for joining. Again, thanks, Aditya, for taking time to go through and explain all these for us, for me and the viewers. So see you again at a future stream. Thanks, everyone. Bye.